we'll start with today's session, which is a poster session 13 on ML applications. Today's chairpersons are Dr. Sudeepan Saha and Dr. A.M. Ramya. We'll be starting with paper 179. The authors are Touseef Ahmad, Anand S Sahadevan, Soumyendu Raha, Rosalie B Lyngdoh, and Deepak Putrevu on superpixel guided weighted low rank representation for nonlinear hyperspectral unmixing. The pattern for today will be 8 plus 2 minutes. So 8 minutes of presentation and 2 minutes for questions. We have Touseef online here. So Touseef, can you just respond once?
Yes, sir. I'm here.
Yeah. Okay, so we'll start with your video.
Hello everyone. I'm Touseef Ahmad, working in Space Applications Center at Ahmedabad. The topic of my presentation is superpixel guided weighted low rank representation for nonlinear hyperspectral unmixing. These are the outlines of my presentation. First, we will discuss robust binary mixing model with low rank constraint. Again, we discuss robust binary mixing model with weighted low rank representation. Then we use sensitivity analysis of WLRR against low rank constraint. Then we introduce superpixel guided scheme for GBO model. Then experimental data and in-depth time discussion. So these are the binary model we use for nonlinear mixing analysis. When we say robust, we introduce here sparse noise term and dense noise term, and we consider in our residual part sparse noise term. So during unmixed process, this model will suppress sparse noise while unmixing the hyperspectral data set. And why we introduce a low rank, because of sometimes our data sets follow low rank properties. So we introduce low rank constraint here with some parameter lambda. For sparsity, we use L0 node, but L0 node is not convex. It will be approximately convex to the using L1 node. This is the final problem. The low rank constraint is handled using SPGD scheme, and sparsity we introduced using L1 node. So this is the model for robust GDM with low rank constraint. Robust GDM with weighted low rank constraint. Here we use weighted because low rank assign equal weight to all the similar values, and weighted low rank assign lower weight to larger singular value and higher weight to smaller singular values. So these are the weightage. How we estimate this weighted? We take inversely proportion of the single value. Here we introduce FL for to avoid the singularities. So this weighted low rank always handle using weighted norms minimization scheme, which estimate rank efficiently and estimate awareness accurately. This is the ADMM formulation which we employed for our model, and this is the benchmark modeling used to people are using for sparse unmixing process. So this is the experimental data that we have generated for nonlinearity. So here we introduce two terms, one is the linear term and another bilinear term. This data set we generated using me at 2018 paper. So we discuss low rank property. So we introduce a 25 mixed pixel with some rank varying XNR. We introduce some noise in band-wise noise and some strips with the real scenario. The 10 mm from spectral library. And bilinear term is also bilinear coefficient we draw in this set 0, 1. So this is the hyperspectral data set for nonlinear emission set. So this is the these are the result for SNR 20 dB and 10 Q properties. Here we just compare our low rank method and weighted low rank method, how it is performed. So here you can see weighted low rank estimating awareness accurately as compared to low rank. They are also varying the SNR of our data, and you can see similar to reconstruction where we are getting better with higher SRE as compared to normal low rank method. So this is our motto to consider weighted low rank constraint to for low rank properties. Now we introduce our superpixel scheme. So So superpixel is a set of pixels which has similar spectral spacing characteristics. There are two types of superpixels here. One is network-based, another like gradient-based. Here we are following network-based method. This is entropy rate superpixel segmentation approach. This approach applied we get superpixels. So we consider each superpixel for our awareness estimation, and we apply Lorentz weighted Lorentz constant over each superpixel to get accurate rank of the superpixels. This is the model we introduce here in awareness matrix. We introduce here superpixels I1 to PP to 1 superpixel, and that model will remain same. And here we same methodology will follow for our solving purpose ADMM. And now we generated our simulated data set, so we can vary the first this is 5 by 4 5 block each block, and we are making all blocks different rank 4 rank 2 rank 3 rank like a previous case like a one block. Here we are we are making a big image, so each block is having a different rank like our in real scenario. We will having some time 2 element values particular superpixels, time 3 element kind of code. So we can get up to 5 rank in each block. This is XCC we have generated. So this means we generated using SNR 30 dB, but we have studied all the data, all the results with varying SNR. So this is also generated according to me et al. 2018. In the right hand side, you can see for case SNR 30 dB case, and we can see that weighted scheme provided significantly better awareness estimates. That is why we have compared robust generalized bilingual missing model with low rank constraint and robust generalized bilingual missing model with superpixel guided weighted low rank. Here we can see with varying SNR we are getting higher SRE as compared to non-low rank constraint. Right hand side we compare 3 popular algorithms. So here we achieve higher SRE with varying SNR as compared to other 2 algorithms, which are used for bilingual missing models. Right hand side you can see, and we see our method provided comparable with that as per other methods. They are the concluding remarks. Here we have done sensitivity analysis of weighted low rank and low rank. We have seen weighted low rank providing accurate result as compared to low rank method. Now then we have introduced this algorithm, superpixel guided weighted low rank constraint, which introduced nonlinear missing and incorporate spatial correlation characteristic of the neighboring pixels, and also suppress the effect of noise during the mixing process. And weighted LRR were significantly better than LRR method, and we have seen higher SRE, lower awareness RMSC, and source RMSC of superpixel guided approach, which confirms the superiority of the model as compared to other methods. These are the references. Thank you so much.
So we can start with the questions.
Yes, do you have any questions? Anyone? Okay, not, then maybe I can ask something. So if possible, if I understand correctly, for this work, your main contribution is introducing the weighted fluoride. Is that correct?
Yes, I'm not able to listen properly.
Yeah,
Do you have
no, like the entire room's microphone is common. Like,
Okay, so I will try to be loud. So Touseef, if I understand correctly, in this work, your main contribution is introducing the weighted fluoride.
Yeah,
Is
weighted
that-
low rank. Yeah, weighted low rank. We have tried weighted low.
So I was trying to understand, like there is a like more well-known paper from 2020, Chang et al., who introduces weighted load and in the context of hyperspectral image restoration, not unmixing. So how is it work different from that, or how is it related to that?
Actually, that paper they are using for sparse unmixing, that is linear unmixing. Here we tried in non-linear case using generalized bilinear model. So that is the only case. Actually, we try to improve that me et al. Paper. It is published in 2018. They use normal low rank transformation for bilinear model. So we tried like let us check weighted low rank how it is performing, and we found that we are getting better significant results. That is our logic here. But that paper you are telling, that is for sparse unmixing. They are using that linear model, but this is bilinear model.
Okay, thank you. Thank you. Can move to the next.
So we'll move to the next presentation. So paper number 31. Authors are Rohit Singh, Mantosh Biswas, and Mahesh Pal. Do you have anyone?
Yes,
any of the
I'm
authors?
Rohit Singh. I'm here. Am I audible to you?
Yeah, you are audible.
Okay.
So the paper is an automated cloud detection method for Sentinel-2 imageries.
And the body of information from which you can be and the object is usually known as remote. So this actually provides imagery on which we can perform some analysis, and there are certain applications that uses these applications such as current monitoring, climate change studies, agricultural monitoring, application of climate modeling, assessment, military studies, and mining resources. And about 67% of the surface is usually covered with cloud. These cloud gets captured in these optical imagery. So therefore, cloud cover detection has a huge importance in dealing with this problematic situation and generating an analysis revenue. Most cloud can be distinguished between based on this certain properties like visibility, transparency, reflectance, brightness, height, and shape. So based on height, we can classify cloud as low, middle, and high. Cloud within the range of 2 kilometers above ground level is usually low. Between 2 to 4, it is usually middle, and above it is high. Low and middle are usually thick, and high is usually thin. How the image is actually captured in optical satellite, that is passive satellite. The sunlight is used. This sunlight is reflected back from the ground, and that reflection is usually Earth envelope that is captured by the sensor and it is sent back to the ground station. But cloud that is present in the atmosphere, you have cloud envelope also, and these get captured, and the light energy that didn't pass goes the shadow. The remote sensing application, extraction and removal of the cloud become highly important. Clouds usually cause district continuity, and the satellite imagery cause blurry and missing information. Blurry with thin cloud and missing with the thick cloud, and similar reflective appearance of cloud and the cloud shadow with the different Earth object usually make it more difficult to effectively make a classification between cloud and non-cloud imagery. So it is highly required that it should generate an effective classification mechanism. And also limited research is reported in this area. So we get this from the literature review that we have done so far. These are the evidences drawn from the literature. There are two types of photography that are for cloud detection, that is threshold based and the machine learning based. In threshold based, a certain rule or certain threshold points are generated that helps us to get that particular pixel is cloudy or not. So these are usually pixel-based classification, both threshold-based and machine learning. In machine learning, SVM and random forests are most extensively used for cloud detection. And threshold-based usually have poor universality, means one threshold working for one image is usually facing some trouble with the other image. So misclassification is there. But machine learning handles this problem effectively. But it requires a track feature exception to improve this feature that is highly important for cloud detection. Feature exceptions such as morphological profiling, bilateral filtering, gray level coherence metrics is usually applied in window, and this actually gathers the spatial information that is required to effectively classify the cloud. We have actually proposed a mechanism that automatically consider the spatial information with the spectral information without requirement of the prior feature extraction through these profiling. Uses better voting Sentinel-2 dataset that have capability and different sites of USA and different areas. We have divided these into training and testing samples, 20 for training and rest for test. See, we are applying our detection method for detection, followed by, instead of using individual pixel, we are creating pixel-wise patches, and each patch is flattened to get the picture. This patch size is usually a odd number, and we are taking the middle pixel, the label of the middle pixel to actually assign the label for the training data. And here for training the classifier, we have used 20 training imageries. So say that the huge computation cost and memory limitation is there. So with the large data set, so for that we have adjusted the training sample with the increase of the text size, and we have trained the classifier to create cloud mask for Sentinel-2 imagery. We don't know what goes approach. We are taking the Sentinel-2 imagery and creating classifier messages and execution simple execution that basically firstly is trained and it's regular is used to train next day and so on, and weighted sample result is actually calculated to generate the cloud mask, and we have also trained random forest and testing. Computing system is used to get the pictures for the each system. And here one something to do with the and we can see that the boost the rank accuracy, which is the highest accuracy and transport. Although difference between the accuracy, although accuracy with the goes with the same is quite very less, but Apple score is highly differentiable. Prediction time is 4 seconds only, and classifier size is quite small. It means that it can be embedded with any system. That we have used different batch size. We have used 50% sample size with one batch size, 25 with 3, 15 with 5, and 10 with 9. And results suggest that with batch 9 we are able to get better features. Means with the maximum spatial information we can get better results. And as for the distance, we would get best result with achieving the 90% overall accuracy and 78% average score. And it is about 6 to 250 times faster than the and also classified size is very simple. The visual analysis of all the test images are there. You can say that the attributes perform very well. The cloud grow quite well. It even for the shadow, it detected quite well. Even if it is for actually and we can see them. But in image 3, some snow is classified in cloud, but this problem persists for other machine learning and other algorithms. We can see that I think we perform quite well, and even the combat result, and we can see in image 8, but it's wrongly classified no cloud as high cloud. So this is the scope of the project. So these are the results that are developed from the visual analysis. We can see for what region it performs quite well. The data progress performs slightly better in thick cloud regions over mountain, and SVM results are also quite good, but from the visual classified. Prove that our proposal is quite better in comparison to other. If we use pixel-wise value, we don't require any feature exception. Although results seem to be better, but there is scope of improvement over the complex feature that have similar reflective index. Therefore, we require novel feature exception mechanism. For a novel feature exception mechanism, we are planning to use position-wise embedding technique that is present in the transformer. We will try to embed these positional information with our pixel-wise patching, and we are hoping that result will be better. That will be done in the future. These are
the question is that how is it compared to S2 cloudless compared to the product that is available?
The cloud masking technique that is available with the Sentinel-2 is actually Send to Core, and I have shown the result also here. But result of that Send to Core, the visual results of Send to Core is actually available in the paper that we have already published. You can check the 28th reference that is provided in my paper. And the tabular format result is also shown in the 12th slide, 11th slide, you can see it, I hope.
Okay, Rohit, I think the question was answered. Question from the chairs.
So, Rohit, I wanted to understand, like, why did not you compare to any CNN-based method?
Yes, ma'am. I think that there is quite a work that is going on with the CNN, and in the paper that we have published, we have actually applied the feature extraction technique that are handcrafted feature with the CNN features. But in the machine learning, this automatically considering of the spatial feature is missing, but it is present in the CNN. So here we are trying to actually provide a method that is quick enough to actually directly consider those spatial features. So in comparison to CNN, this technique is quite faster, and it can handle a large amount of data with the computational cost that we currently have. So I'm just by this paper, I'm just trying to give a direction that can be possible, so that we can apply the machine learning that is quite faster in comparison to the CNN algorithms that we are actually focusing. I also have other paper by using transformer. That's why I'm trying to take some key points from the transformer to actually enhance the mechanism that I have currently proposed.
Okay, we got that. Thank you. You can.
Yeah. Okay, thank you, Rohit.
Thank you.
So we'll move to the next presentation. So that's paper 117. So Jayantrao Mohite, Suryakant Sawant, Ankur Pandit, Prakash Kumar, and Srinivasu Pappula. Is anyone here? Yeah, so the paper name is Sugarcane Area Mapping with Zero Labels using Hybrid, Unsupervised, and Supervised approach.
I know those, they have. Oh, they have not.
Okay, a similar problem happened. So we'll move on with the next paper. So that's paper 247. Authors are Geetika Burman and B.S. Dayasagar. Yeah, you can come. The title of the paper is A New Approach to Compute Vector-Based Morphological Features for Classification of Hyperspectral Image.
I'm Deepak from Indian Statistical Institute. Today I'll be presenting a new approach to compute vector-based morphological features for classification of hyperspectral image. It consists of hundreds of spectral bands. It can capture fine spectral details of different objects. Often the presence of mixed pixels, complex spatial information, and higher dimensionality, hyperspectral image needs mathematical models to extract meaningful information. And here, mathematical morphology plays a crucial role in analyzing the spatial information of objects in these images. Logical operator, the primary operator dilation and erosion are primarily defined for single band images or binary images in graceful images, which uses infimum and suffimum to define the operators. For hyperspectral images, pixels are represented by vectors, requiring an extension of mathematical morphological operators to these images. In previous work, traditionally, hyperspectral images are broken down or projected into monoband flexible images or to the first few bands of images using principal component analysis or minimum noise extraction. And then they are applied individually to each band, later reassembling the result. However, this can introduce the pixel factors to use are not originally present and disregard the band population. Extended morphological operations have been applied to spectral domain using vector-based approach, where mathematical morphological operators are applied to the entire image band as a single block. But creating an unambiguous ordering process for vectors still remains a challenge. And in this work, a vector ordering strategy based on morphological distance or dilation distance is proposed compute a multi-channel morphological profile. This method aims to find the supremum and infimum of pixel vectors in local neighborhood. Also, consider the correlation between bands and preserve the original vectors. This approach is based on defining a priority factor across the band. App data hyperspectral image with n-dimensional pixel vectors and has two pixel vectors application x, y, and x plus y this, f of x, y, and f of x plus y this, which are two n-dimensional pixel vectors. Our methodology aims to compare two vectors f of x and f of x plus y this based on the weighted sum of the respective bands. To compare these vectors, we propose a weight vector for each band R in hyperspectral image, which is defined as W of ith band as the summation of the dilation distance of ith band to all other band. Distance between ith band and jth band can be defined as the minimum of n such that of the nth dilation of ith band at different level lambda by flat structuring element V, it becomes greater than the jth band. And NV is the end span dilation of structuring element V. The generalized dilation distance is the average of the dilation distance at different level lambda present in the image. Finally, the two vectors can be compared as f of xy is greater than f of x plus y is if the summation of all the weighted vector components of f of xy is greater than the summation of all the weighted vector components of f of x plus y is. The proposed ordering strategy might equate inherently distinct vectors. So an additional ordering strategy is proposed, where we consider the band with maximum weight as the highest priority band. Then to resolve the incomparability using the previous ordering strategy, the vectors are compared based on the highest prioritized component. If that is equal, then based on the next prioritized component and so forth. Now, using this strategy, we can define supremum and infimum of a set of vectors as the greatest vector as supremum and the lowest vector as infimum. And based on this, the multivariate dilation and erosion can be defined as follows. And we can also compute the multivariate morphological profile using this ordering. Computed the features observed in multivariate morphological profile using the proposed vector ordering method that was subsequently used for classification using support vector machine. We employed the Fabian University Hyperspectral Image dataset consisting of 9 classes and 115 ranks. Since the morphological profile is dependent on the number of openings and closing cycles, empirically we have decided the number of opening and closing cycles as P3, where the classification accuracy is optimal. In this figure, figure A is ground truth map of area university and B corresponding to the classification map obtained using the proposed approach. To further evaluate our proposed method, we compare the classification results obtained using our strategy against two other widely accepted vector ordering strategies. One is lexicographic ordering with increasing priority, and the other one is lexicographic ordering with decreasing priority with multivariate morphological profile. The corresponding classification map for all three methods along with the given ground truth map is shown in this figure. The figure A is the ground truth of the dataset, and B corresponds to the classification map obtained by computing morphological profile using the proposed vector ordering strategy. C is the classification map obtained by computing morphological profile using lexicographic ordering with increasing priority, and D is the classification map obtained by computing multi-channel morphological profile using lexicographic ordering with decreasing priority. Quantitative comparison, we have used two metrics, overall accuracy and purple coefficient. A summary of results for all three methods in terms of overall accuracy and purple coefficient is given. From here, we can observe that classification using the proposed method outperforms the classification using other two methods. We have explored a vector ordering strategy based on dilation distance for computing in multi-channel equivalent profiles for classification in perspective image, and also demonstrated superior performance of the proposed strategy in comparison to other methods, and exploring the applicability of the proposed approach in various multi-channel morphological operations for multi-channel images is a future research, and also investigating applied in processing states before classification is another topic for future research. Thank you.
I just had one. That that correlation between the bands as preserved. How are we validating that correlation is preserved here?
Actually, the dilation does not have a region, so it's already very long in the gradient of our work. So there, it has been proven validated the dilation is going to be started up to 2022.
We also have a question online, so I will let you answer that from chat also, so that we can take any other questions here. Yeah. Oh, it's fine.
We have that, right? Because one of the presentations was from there. So you can ask.
Okay, yeah. So the question is, what are the unique challenges and opportunities for using vector-based morphological features in specific application domains such as precision agriculture, environmental monitoring, or mineral exploration?
Yes, exactly. What happens when we consider the pixel like this in case of hyperspectral images? So there is a very high chance of mixed spectral signature. So when we preserve the picture vectors, or when we consider when we consider the special features, so we can addition to the spectral signature, spectral feature, we can also consider the special features. So it gives more accuracy in terms of vegetation or urban area classification in this. So we have to obviously fine tune all those things.
Okay, I hope that was audible and satisfactory, Touseef. Any other questions?
Accidentally because you are within the classes, how this method, for some classes, will define and some classes, I almost what experiment I do balance class. No, I mean the final accuracy that you are mentioning will be overall accuracy, which is shown that it will increase from 85 to 92. Oh, I will other matters. So what about the individual classes? That would give you a better interpretation of how this method works and how your teacher.
Did you see like the variation between the different classes between different like for some classes?
Not much variance actually. So it's since I have told you I have balanced class number.
So that's why, but still it can be the case that.
But yes, but not. I think with one class it is little bit of but not too much. It's like up to 5 to. Why not? How do you relate that to the spatial feature that you are extracting? Okay. So actually in this image maybe that because of some noise present which is similar to that specific class of so which is maybe the sample removing that might be important. Yeah, it's a nice solution also.
We'll move on to the next paper. Thank you, Geetika.
Thank you.
Oh, yeah. So the next paper is 164. The authors are Surya Suresh and Arun PV. So, you are your name? Surya. Okay. So the title is Unmixing in Latent Space, a novel unsupervised approach for geological mapping of lunar surface.
It depends on our work on unmixing in latent space, a novel unsupervised approach for geological mapping on lunar surface. I would like to express my sincere thanks to InGARSS for this opportunity. I would like to extend my heartfelt thank you to my co-authors, Dr. Arun P. from Prakash Kumar and Dr. Ankur Pandit for their invaluable contribution to this work. Hold significant importance to remote sensing, environmental monitoring, agriculture, geology and geography, defense and security, planetary exploration, etc. As we dive into this topic, several limitations and challenges are there to deal with hyperspectral images for animals. Agenda for this presentation. Introduction. Spectral unmixing is crucial in hyperspectral image analysis. And this slide, limited resolution and spectrum. Slide is lunar data from more meteorological cycles on Chandrayaan or spectral unmixing analysis. Uses in current spectral unmixing methods for planetary data includes noise, limited samples, and high dimension. Comprehensive evaluation considers accuracy, computational expenses, explainability, generalizability, sensitivity to knowledge, and training capability. There is linear and nonlinear methods. An introduction to an innovative auto-encoder-based approach for hyperspectral image analysis. That encoded representation for data reconstruction, reducing dimensionality, noise, and extracting relevancy. Objective is to introduce an innovative auto-encoder-based spectral imaging method for hyperspectral image analysis, leveraging encoded representations to understand this noise and high dimensionality. The approach aims to enhance accuracy in abundant estimation and enable extraction, particularly in scenarios with a limited time. The survey, these are the benchmark methods we use for spectral unmixing after encoding operation are facing challenges of knowledge, high dimensionality, etc. Post method, the study's auto-encoder-based method introduces a novel approach, leveraging encoder data to reconstruct the original data into latent representation or hidden representation. Subsequently, employed for a number extraction and abundant estimation from the scene. This is our model's architecture. Here we are treating the input as lunar input data as input. Then first we will do some expressions here. This is data like the data normalization, solving, picture extraction. Then we will use the reprocess the data to the autoencoder. Basically, the autoencoder consists of encoder and the decoder. Here we are only using the encoder network for reconstruct the data. This architecture consists of fully connected feed-forward neural network. Using our data, the autoencoder model is constructed using Keras sequential technique. The architecture consists of an input layer and the input. This encoding layer reduces the dimensionality of the input data to the specified encoding dimension. Further, generates approximations of the original input by utilizing the learned context representation. To enable reconstruction quality, the original test data is initially compared with the reconstructed data. This includes analysis cases, the autoencoder capacity to fully capture and achieve accurate returns. After that, after you will get a reconstructed data in our representation, the bottom is layer of the encoder. This image is generated in planar library. And apply this data to the benchmark model test IIIT-B, that is the vertex component analysis for inverse extraction and fully construct discover method for abundant estimation. Next method is the CNN-B convolutional autoencoder that leverages hyperspectral data, spectral and spatial data. Next method is the autoencoder network approach. It utilizes sparse and autoencoder network encoding sparsity and nonlinearity for inverse and abundant extraction. Next method is the union and distribution. The computational knowledge for spectral dependencies and log capacity. Next method is the non-simple convolutional network for deep hyperspectral unmixing. And next method is the PP1 method, the polynomial nonlinear mixing method for nonlinear unmixing. Bracket n numbers after applying data benchmark model. This is using personal data, that is the input data applied to this model and also the input data in the application. The abundance map of those data. As an evaluation procedure, we are using RMC and STAR. RMC is a metric used to assess the accuracy of automatic estimation unmixing. As longer the RMC indicated data points, displaying higher accuracy in quantifying the contribution of the engineer. Then STAR is another method used to detect variety mixing. estimated N members and subsequent N members. As smaller the part value we expect, better means. Then from this table, in our analysis, it reveals that RMSP and star value exhibit significant improvement in latent space data and compared to the original data. This suggests that employing the latent space data for spectral unmixing technique increase the accuracy for end construction and RMSP distribution. Conclusion: introduced an innovative autoencoder-based feature for refining and extracting and abundance distribution. Extensively evaluated on Lumina data to enhance the accuracy by reconstructing original data into non-original representation. We got a promising results demonstrated on abundant effective in modeling enablers, particularly in challenging lunar data, knowledge and lunar standards. Mainly, here we are overcome issues in lunar data by improving the unmixing process in the case of the further responsibility. But we need this opportunity and for accepting.
We can start taking questions.
Madam, can you show some mapping? Where are mapping, geological mapping, mineral mapping in unmixing, where you have shown? And how will you generalize your approach?
Can you repeat that question again?
So,
I'm not able to see that mineral map in this presentation. Can you show me that slide if you are having end member, mineral end member and map?
the animal extraction, that's right.
Okay. Which slide is this?
You mean this slide, right?
Yeah, then how did you identify these end member? Means you compare with the spectral library, yeah, how you can say particular end members, these minerals, how can you say which one?
Means I extracted these end members using some of the techniques like VCA and Finder algorithms.
Now you extracted from image, but how will you identify? How will you label each end member?
Okay, this is an unsupervised method.
Uh,
So we are just extracting minerals. Then we are just plotting. Then we are finding the fraction of that minerals.
Well, how do you know like how many minerals there? How many you have to give some numbers na in your approach?
Yeah, we are extracting 4 minerals.
How do you know there are 4 in this image?
Yes.
And how will you generalize this approach? Like it will perform in all cases.
Could you please repeat the question?
How will you generalize your approach? You have tested your approach in one scene. How would you generalize like your approach is significantly comparable with other methods? Yeah, better.
What I did is first I will give the input to the encoding part of the autoencoder. Then it will reduce the dimensionality and also it will extract only the relevant features. Then we will do the spectral unmixing. We will get some accurate result comparing to the already implemented some benchmark method.
So let's move on.
Okay. Okay, it's okay.
Yeah, it's a bit like going in the different direction.
Okay.
My first question is a bit related to actually what he was asking, but slightly different also. So what I don't see is that like what's related to lunar. Your paper especially stresses on the lunar word, right? So what's related to lunar here? Like this method, I don't see anything which has to do anything with the moon, right?
Means they're using the lunar data, sir. The mineralogical mapper data.
But it could be applied on any data, right? Like
yes, we can use that for some Indian pines data. That is such a data.
So the other thing is more methodological. I don't understand. Like so you are taking the auto-encoded picture.
Yes,
the bottleneck features.
Yes.
That's fine. But then you are just combining it with some existing methods like MissingNet and all.
Yes.
But let's say like if you talk about MissingNet, it also has like a full CNN encoder decoder architecture, right?
It is there, yeah.
So if you just take a part of your architecture and fit into, you just appended it before the MissingNet's decoder, or how did you append it?
First what I did, first I took the data, then I put it into an encoder part.
You have the open
Yes,
picture, I understand
yes,
it now. How did you combine it with MissingNet? Because it also has an encoder decoder part, right?
Yes.
If you train again with MissingNet.
Yes, I will train again with the MissingNet, with the encoded data.
Encoded data
Right.
with the MissingNet.
Yes.
Input.
Yes, yes. Then we will get this,
I see. Question is same thing because for Luna and even your methodology and also Indian prime
Yes,
data.
yes,
So that is something. And like again, Luna data, so what are the classes? Like what are you trying to identify in the image not here? Like, okay, class 1, class 2, class 3 and class 4. But this is the Luna data, right? Like what are the minerals that you are trying to identify? And what is the accuracy for each identification?
Ma'am, my main aim is to how we can extract the N numbers. Then after that, we can compare it with some of the minerals in that area.
But in the same lunar M3, we have like lots of other hyperspectral unmixing methods are available.
Yes.
So the same data set.
Yes.
So you could have compared with that, maybe in future.
Okay, okay, sure, ma'am. I will try. Thank you.
Thank you, Surya. We'll move on. So we have paper 84. The authors are Yash Mittal, Uttam Kumar, and Diksha Agarwal. The title is Online Incremental Machine Learning Model for Multi-Sensor and Multi-Temporal Satellite Data, a case study of Bangalore. So we have Yash.
I'm Yash Mittal. I'm a student of IIIT Bangalore, and I'll be presenting the paper Online Incremental Machine Learning Model for Multi-Sensor and Multi-Temporal Satellite Data. First of all, introduction. Once a model has been trained and deployed, training it again on a new and different set of data is time and compute expensive. In our research, we try to address this limitation by enabling the continuous learning of land use patterns over multi-sensor and multi-temporal data. Incremental learning allows models to adapt to evolving landscapes, automatically incorporate new data, and refine their classification capabilities over time. And data. So we are here considering greater Bangalore sensing data, which is obtained from USGS Earth Explorer data repository. And 4 classes are considered for classification. The first is urban, which covers building rooms and paved surfaces. Second is vegetation, which covers parks, botanical gardens, forests, and grasslands. Third is water bodies, which covers sewage treatment plants, lakes, ponds, and next is others, which covers everything else, like lake, from quarry regions and that. Okay, that's it. We have taken data from 2017 to 2022, and several geodetic images were pre-processed using Python libraries like Rastrile, Visual Spatial Consistency, Resolution Alignment. The common bands from LT05C to L1, LT05TM, and LA4LI were considered for classification and purpose analysis. So basically, they're considered 5 common bands from each of these 3 different sensors, and these were considered for all our studies. Training test data were collected for each year. So as you can see in this slide, data from 3 different sensors are collected. For 2007, data comes from this sensor. For the next 3 years, the data comes from different sensor, and all other years of data comes from LHO. And now coming to the methodology. So here we have divided our experiments into different parts. The first is classical offline ML model, and the second is incremental online ML model.
further subdivided into two different approaches. First, we are doing experiments for a single year, and then we are doing it for multiple years of data. So initially, we trained classical and offline ML model for different years of data, like 2014, 16, 19, and 22. Next, we train these ML models using a joint training approach, which means that training data of multiple years were combined and used for training. Example, data from 2009 to 2014 were combined and utilized to train ML model and subsequently tested on testing data from 2014. Random forest classifier from scikit-learn package was deployed for training this model. For implementing organic ML model, we did similar experiments like classical model. We did the similar experiment for single year and next for multiple years of data. Data for each year is parsed individually, starting earliest year and chronological. Example, training data for year 2014 were processed first, followed by subsequent years up to 2022. This model is then evaluated on test data of year 2018. Here we have used adaptive random forest, which comes from the package. And here are the results for the same. So if you see that we are showing here the results for a single year, and the comparison is done for traditional method and incremental online. In most of the cases, our incremental online method is performing better. Except year 2016, where we have 0.89 accuracy, means 89% accuracy in traditional offline method and 88% in. Apart from that, you can see that 67% is there in 2014 and 68% is in 2014 for incremental method. For 2019, we have 60 here and 62 here, and for 2022, we have 62 and 63. If you see precision, we call an S score for traditional and incremental method. The same observations were done. Generally, incremental method is actually performing better than the traditional. We can see the results for multiple years of data. Here in experiment 1, we are taking the data from two different sensors, and the data is coming from 2009 to 2014, and the data is used for testing is 2014 data. We can see that in traditional method, we are getting around 55% accuracy, but for incremental online method, we are getting 66% accuracy, which is a huge difference. In experiment 2, we are taking data from three different sensors starting from 2007 to 2016, and 2016 test data used for testing the model. We got 86% accuracy here in traditional method, but in incremental method, we got 87% accuracy. In experiment 3 and experiment 4, we are taking data set from a single sensor, and here are the results for the same. We are testing it on 2019 data and 22 data. The accuracy is 58% and 62% in incremental online method. Here it is 59% and 65%. So we are seeing consistently that incremental online method is performing better. The same has been observed for precision, recall, and effort score too. We can see that there are predictions for random forest and predictive random forest. You can see that random forest is getting confused and predicting a lot of pixels as others, which can be vegetation or other classes. Incremental online method perform reasonably well in terms of accuracy, precision, and recall when compared to traditional offline method. Geospatial data is dynamic due to its ability to capture temporal changes, seasonal variations, dynamic phenomena, and therefore is suitable for online learning. Online learning also allows us to use resources efficiently, where all the training data is not required to be memory while playing. Also, we have two limitations for this. Data imbalance also cause problem, and if in data sheet erroneous or misleading data is fed, the performance will decompress, and the battery lose. Thank you.
So we can take questions? Any from the audience?
Okay, so not, I will go ahead forward. So my main concern is that, I mean, what I see that you are trying to prove is that online incremental learning is better than offline learning.
If we have different satellite data, we can use instrumental online learning to
Yes, yes, that's understandable. Taking the different types of bands from which to answer. But my main concern is that I think this is not known to the public, right? That I mean, there are several works on the online incremental learning in the university community, starting from quite well-known work of Julia Taravalka in 2019. So what's new like here? So you are, I didn't see any methodology. So it's your methodology is a random products from the inner package. Is that the methodology?
No, sir. So basically, there is not much literature on this, as far as I know.
No, not really. It's not like, of course, it's not as hyperspectral image classification or something like that, but there are literature. Maybe not hundreds, thousands, but there are numbers of tens.
So basically, my approach was just to show it in the experiment that that incremental learning can be used for this type of data, where I have used 3 types of satellite data. And I've not used all bands, so basically I've used R, G, B, and NIR and SW1. Only 5 bands are used to get these results. So in the limited bands, I have got these results, and I've seen that like incremental online learning is performing well. And also shown that basically in my, there's not detailed one, but in my research I have shown that that basically when we train it to simple traditional approach, we need a lot more computational power, right? So even if the satellite data is quite cumbersome, right? It is very not easy to handle it a lot of data at a single time. So in my approach, I have shown that with limited resources, you can actually get better accuracy.
Yeah, your message is clear. It's not only the that something data is too much really important. It's also that it's coming in states.
Yeah.
So the data for 24 is not yet available. Some new sensor launches in 2024.
Yes.
You don't want to scratch for that sensor from 2024.
Yes.
So we can use the whatever sensors we have till now, and we can start from there. So your message is clear, but slightly more methodology of it. But that's right.
It's all 30. Yeah.
Finally, one of the accuracy sites, the experiment is having a very high
So, to what I have observed, basically, as I've shown in my limitations also, as we have class imbalance, right? As class imbalance goes higher, the performance of these incremental learning approaches decreases. So, in the other class where you're seeing that, I remember there is a class others, right, which I have taken 4 classes, so in that others class is causing us trouble. So when I have so basically, yeah, so correct. So in my all the experiments, the classes are not same. So it's like for year maybe 2014, I have 100 samples of class A and maybe 80 samples of class B, right? So the label data which I got is not equally balanced for all the years. So in the years where the data imbalance is more, the performance is degraded in the incremental learning, and it is like degraded too much high.
training data that you have created?
Yes, we have created.
Thank you, Yash. We'll move on to the next paper. Paper 236. The authors are Amol Patil and Kedar Kulkarni. Amol. So the title is Hybrid Machine Learning Numerical Weather Prediction Approach for Rainfall Prediction.
Good afternoon. I am going to present our work on a hybrid machine learning numerical weather prediction approach for rainfall prediction. Introduction. prediction is extremely important to us and inform decisions to adapt to floods, droughts, to do the agricultural activity planning, and to manage the water resources. The major sources of rainfall for this type of applications coming from the remote sensing and numerical weather prediction models, where remote sensing data is only available at near real-time basis. From the numerical weather prediction models for this lot of uncertainties. That may be because of the initial condition uncertainty, like observation errors and coverages, which causes the model to drift from the reality. And coming from the model uncertainty, where unresolved states and model physics affect the accuracy of the predicted rainfall. With the recent technological advancements, machine learning has become a viable substitute for complex numerical modeling systems. Therefore, the main aim of the present work is to evaluate the potential of machine learning to improve the accuracy of rainfall forecast using forecasted atmospheric variables and ground station observations. The outcome from this work is expected to facilitate early decision making to stakeholders and to improve the usefulness of remote sensing based rainfall products as well by merging and assimilation techniques. Coming to the datasets, rainfall data in this work is from Global Historical Climatology Network, which is available at daily timestamp. From 55 Geoscience sessions in the total were used between June 1st and September 30th, 2015. Of these, 18 stations were used for independent validation, and the remaining 37 stations were used for training the model. The next data set is the global forecast system, which is a full global scale numerical weather prediction system. Global analysis and performance. Divided spatially by 0.5 degree by 0.5 degree grade, and the vertical resolution is the 26 layers spanning from sea level to troposphere. The model is initialized at every 0, 6, 12, and 18 hour UTC, and it produces the forecast 3 early below of 58, 384 forecast hours. To build the machine learning model from GFS forecast, we have used two approaches for the feature selection. In the first approach, we have used the data-driven approach where correlation more than 0.3 has been used. In this, we found 7 variables at 46 different atmospheric levels. Then, in the second approach, we have used the knowledge of the physical process where we have used 4 different variables. And therefore, in total, we have used 50 atmospheric states for training our machine learning models. The overall methodology shown here in this workshop. We will discuss each one in the next slides. Machine learning formulations. We have used 3 different machine learning formulations in our study based on type of application. Primary classification, rain, no rain. Division of the rainfall for binary classification. Class classification, where we use IIIT guidelines for dividing the rainfall into multiple classes. And here is the distribution of those classes. I use the regression analysis to predict the rainfall intensity directly. The weather prediction model provides nowcast and forecast, where nowcasts are computed by assimilating globally observed data into atmospheric model are known to be more precise than forecast. Therefore, in this study, we consider 2 different feature sets: FS1, which uses GFS nowcast alone, and FS2 uses GFS nowcast and forecast at 6 early interval until the lead time of interest. We have used 3 different machine learning models. Yes, artificial networks and extreme cloud system. Training independently for each day lead time up to maximum 7 days lead time using 37 Geoscience station function. Use scaling and hyperparameter optimization in standard way for each model training. And then we have tested the training models using the datasets from 18 Geoscience test stations. Binary and multi-class classification have been evaluated using accuracy and weighted outcome score. Models were evaluated using a mean absolute error and R-square. So the results, plots. The top 2 plots show the results for the FS1 dataset where we have used only nowcasted information, and bottom 2 plots show the datasets where we have used nowcasted as well as forecasted information. On the left, we see accuracy. On the right, we see outcome score. So for rain or rain binary classification with FS1, the prediction performance of all the ML models become worse than that of the GFS baseline after day 2 itself. Whereas the FS2, all ML models outperform the GFS baseline for all day lead times. However, the accuracy of all classification models utilizing FS2 decreases in lead time, because atmospheric forecasts are expected to lose its accuracy as their lead time increases. The results are organized the same way for the binary classification. Here we can see that the accuracy score for FS1 dataset as well shows significantly high accuracy. That may be because of the imbalanced dataset of the rainfall for the multi-class classification. Therefore, here we have plotted the weighted F1 score. But still, we can see the weighted F1 score shows significant improvement over GFS baseline for FS1 as well as FS2 scenarios. You can see that F1 score for FS1 declines faster with the lead time than the FS2, which is consistent with the rain volume classification figures. The exhibit systems consistently outperform the other machine learning models used across all lead times. Analysis. All the machine learning models outperform the GFS baseline in terms of R-square for FS1 model. However, the models could not improve the mean absolute error from the secondary lead time. In case of FS2, the XGBoost and neural net consistently outperform over the GFS baseline. So MA and R-square statistics, we can see the performance improve. Among the machine learning models, the neural net has outperformed others in terms of mean absolute error. This work presents a novel machine learning-based hybrid approach to predict the rainfall that effectively leverages atmospheric nowcast and forecast information from the GFS. Following are the key conclusions. The use of both atmospheric nowcast and forecast as machine learning features to predict the rainfall shows good potential in surpassing the prediction performance of the GFS baseline. The proposed model shows from 13 to 25% improvement in the prediction accuracy for binary, multi-class, as well as regression techniques. ML models perform equally well for weight knowing classification. XGBoost and neural net perform the best for multi-class classification as well as regression expected.
You can start taking questions. Yeah.
Yeah. So I was just wondering, what's your resolution of your predictions? Because GFS is 0.25.
Yeah.
So
when
you predict how much?
Yeah, at 0.25 only, because the thing is, like, we tried to use IMD data because it is already at 0.25. But the problem was that there are multiple pixels in IMD data which are having no rain gauge at all. So we did not get that information specifically which should select. So we directly took the Geoscience station data and filter out those stations which are having inconsistencies. So we cross-check with the IMD and other data sources, and then we decided to use these 55 stations.
So the baseline will be like IMD data, like to validate your answers.
Right now we have divided the stations. So independently, we have applied to totally different stations as I shown in the map. But yes, in the future, we would like to extend the time series, because this was really data intensive problem. We just downloaded 7 days lead time from the GFS for 4 months. Now we have a time series of 3 years or more. So we would like to divide it temporally.
How far are you able to predict from?
Yeah, so right now we are doing for 7 days. We stuck there because of the data limitations, but we can see the regression approach is still predicting better than GFS, up to 7. So I guess we can go little more than 7.
Okay, just like one more question. So DeepMind also released a GraphCast.
Yes.
So for that, they're using NR5 dataset, which has 37 questions.
Yes.
Compared to like
yes.
So any
the thing is, yes, exactly. So right now GFS is having 64 pressure levels, because this study we did at 2015. So when we access the archive data for the real-time forecast from GFS, so this data is actually having 31 layers or something. We selected 26 out of them. Yeah. So when we will do the next study, we will definitely select large number of variables, or sorry, multiple pressure levels, whatever maximum available. Yeah.
Any other?
from the computation person, how does this improve?
Yeah, so the computationally, right now we are not using any sophisticated clusters or anything. We are still doing job on our maps. So right now, because this is still a linear problem, we extracted these features for those stations. And then we created a large matrix. It takes a couple of hours to train, of course, but yeah, this is right now we are managing. But soon we will be having a computing cluster, then we can run on 2-dimensional space. Yeah, so I think I'll show you the slide quickly. Yeah, so here are the variables which we selected using multiple ways. So we use the data-driven approach and selected the variables which are from this. Yeah. So already there are more than 500 features. So we selected these 50 out of those 500, 555 something. So we selected only these, and we also removed the features which are having cross correlation, high cross correlation.
Right now, your approach is more using like a spatial correlation, spatial correlation.
Right now, no. Yeah, right. So the basic idea was to get the one-day prediction from this machine learning approach, because atmospheric models are known for having good prediction ability for relative humidity or atmospheric variables. But the rainfall prediction hampers because of some cloud microphysics schemes, or because those processes are very difficult to capture by physics-based approaches. So we have found, like for our testing 17 stations, there are more than 10 stations where one-day lead time precipitation itself is giving better results statistically than TRMM estimates right now. So we can have these two products like data merging or simulation applications together. Yeah, thank you.
Thank you, Amar. So we'll move on to the last presentation for the day, paper 268. The authors are Satya Prakash, Jayan Vijayan Singha, Sunil Nautiyal, and Michael Wachendorf. The title is A Systematic Procedure for Land Use, Land Cover Mapping with Remote Sensing Data and Machine Learning. So you are Satya Prakash. Satya Prakash.
I'm a PhD friend at the University of Kassel, Germany, working under the supervision of Professor Sunil Nautiyal and Professor Mantosh Biswas. It gives me immense pleasure to present my work on this prestigious platform. So I'm going to present on the topic of systematic procedure for land map using reputable machine learning model with set activity. The co-authors of this research are Dr. Jayantrao Mohite, Professor Sunil Nautiyal, and Professor Michael Wachendorf. Sensing satellite images and machine learning models are currently utilized to generate land data. As we all know, machine learning algorithm has gained significant popularity in spatial mapping and environmental analysis. These algorithms are excellent at recognizing complex patterns and relationships within the data. However, machine learning model does not substantially consider the spatial autocorrelation effect of remote sensing imaging. Considering spatial autocorrelation is crucial task in remote sensing because neighboring fields often share similar environmental characteristics. While ignoring these correlations may lead to models that overlook important spatial patterns, potentially resulting in less accurate predictions. Interpretation challenges in machine learning model development and prediction analysis very challenging. Machine learning models are difficult to understand because of its complex patterns. They are considered as a black box where user can only observe the input and output without understanding how the model predicts the result. One recently developed two methods for the interpretation of machine learning models, sharply adaptive explanation and local interpretable model line are used to explain any black box. Estimating uncertainty when applying models in unseen spatial and temporal data very much challenging. Since spatial mapping requires prediction to new geographic locations or unclassified cases, which often goes along with new predictor properties. Measuring how these similar predictors at new locations are found to in training is important. Objective of the credit study is to develop machine learning models to map landed land cover by
accounting for the spatial autocorrelation design, and to interpret the developed models and explain the prediction, to estimate the model uncertainty for the prediction at unseen data. The present research was examined in Bangalore district. The district was selected for the study based on the project experimental set. As I am a part of the Indo-German project collaboration, DBT and DHG, this study area is selected for rapid growth in northern part of Bangalore because of establishment of urbanization activity and to understand the development in different zones, urban transition and rural areas. We have used this for satellite images which were acquired on 26th of February 2021, which had 5.8 meter spatial resolution and it has three spectral bands, green, red, and NIR. We have collected 3,404 sample points for 7 land use plants, crop and build-up, fallow land, forest plantation, grass, grazing, and water bodies. Total of 16 spectral variables were utilized and and 3 machine learning models were tested: random forest, extreme gradient boosting, light gradient boosting machines. The model developed two superior techniques: random cross validation and spatial cross validation. The aim of using spatial cross validation was to remove bias due to spatial autocorrelation in the remote sensing data. Based on the cross validation modeling results, the best modeling algorithm was managed. The identified best model was further investigated to explain its behavior using SAP values for correct and incorrect prediction of SAP separately adaptive explanation is basically based on the same theoretical approach to explain the output of any machine learning model. Finally, the uncertainty of the prediction from the best model for the whole image are explained by computing the similarity index and area of applicability. Coming to the resultant discussion part, we have compared all three models: random forest, XGBoost, and LGB. The XGBoost model saw the highest overall accuracy for both the cross validation methods. It was clear that the spatial cross validation model accuracy were less than random cross validation because the spatial autocorrelation effect could be removed in that spatial cross validation. So for the interpretation of model, we have selected XGBoost because of its high accuracy. Using SAP value for model interpretation, this figure will to know mean SAP value impact on each feature of the model across all instances of the data. This plot indicates that the normalized green NG indices hold significant importance for filter class. Green when P1 and T hold significant importance for forest class. And similarly, we got to understand that which feature is important for each particular class. Understood the data mix correctly and incorrectly between the model for each feature. Figure indicates the SAP value plot for one instance from the problem class, which was correctly predicted. The near infrared band, BI windbreak band, 2 band, normalized near infrared positively impact this instance. In this observation, the near infrared band value was 0.26, which was higher than the average value for the problem class. And it is fact from various past studies that the near infrared has the highest reflective. For the green and the vegetation, it would become an essential variable to discriminate problems from other classes. It has been observed that the prediction value for this instance of data of crop class is 5.3, which is greater than the base value 1.6. Therefore, this data instance predicts the model with high performance and produces high accuracy output for crop class. In figure B, the length of the bar is always in negative direction. The near infrared band was positively related to the problem class, but it is lower than the average value for the problem feature given one fact. Therefore, it tends the prediction plausibility. The prediction value is lower than the base value 1.6. In this case, and this row of crop class data has been predicted incorrectly. But the model uncertainty for the prediction for the unclassified. The figure represents first a satellite image, then A land use land cover, then B the similarity index, C area of applicability. The DI showed spatial patterns across the study area. There are the values ranging from 0 to 4. The pixel with high DI value indicated that remote sensing variables from those pixels were substantially distinct from the training data. The prediction of those pixels might be highly uncertain. The finding indicates that the high values are low applicability in this study area, which means that this area features very distinct environments compared to the environment covered by the training data. It has been clearly observed that the pink highlighted regions in the DI image are exhibiting high values, which are highly segregated from the attributes. The figure C AO finding shows that 90.5% of the pixels were within area of activity, which explained what pixel remote sensing variables were similar to the model's training data. In figure C, we can see the distribution of the area of activity values over the study region alongside predicted result. While the highlighted dark regions are not correctly predicting the variables, since the dissimilarity index of that particular region is also exhibiting high values. The non-identified pixels are different elements as compared to the selected feature class. Home message from the study incorporating special cross validation has contributed to the establishment of a robust model. Employing set-based interpretation methods offers a better understanding of the black box machine learning model, and utilizing AI values and AO provide model prediction and stability on the grid. Thank you.
We can take questions from the audience. The chairs can be.
So, do you have like any reasoning behind like the methods that were used here?
Actually, my thing is I want to explain the machine learning model, the basic behind the reason to how the like we are taking so much of training samples, but we are giving the input. For example, you are using train test split data. We don't know like you are giving some sets of data for training and other sets for validation, but you don't.
And the methods that you have chosen in this case, what did you choose them?
Okay, like random forest execution, light given. See, I have done some kind of literature review, so there, I got to find the some of the research articles which show the random forest is good for the like good for the land cover classification, and nowadays executes performing much better result than the random forest. And after some time in 2017, it came light GVM gradient boosting machine. So in that particular manner, I've selected these three models.
So one more just suggestion, the spatial activity of the uncertainty that I mentioned. That part is also has been looked by the community in the last few years, quite a lot actually, more in the context of deep learning. But the way the machine learning models, the more traditional machine learning models that we were working with, so for that you could look into this paper, will be helpful for the research. From the group of Annamya, she's a
Hannah, yeah, I followed one article.
Yeah, so did you follow this one, the predicting permanent space?
Yeah, this one. From there, I got knowledge of this thing.
Okay, you already followed that paper. So that's one useful paper. Then
Yes,
there are
yes.
several other
Yes.
papers which are more into the deep learning, so not really applicable for you, like the line of work that you are doing. But I think it's better that you actually graduate to the deep learning, right?
Yeah, after this, because I'm new in machine learning model, so this year I will started. So after that, my plan is to move to deep learning
So
one
when
year.
you move to the deep learning, then there is a paper from which is authored by me, and first author is Kauri Koski. You can look into that also.
Okay, sure. Thank you.
Like, at the sharp features, in that, lower to that, like NVDA has no, less pages. Why do you think that is like, I mean, major?
Because there are so many parameters which are providing more good kind of factors for the features, because and we are in comparison to that particular features not able to define that, because I'm provided to define vegetation there, and I are performing much better than the NDVI. But maybe sort of it's kind of, you can see the band depend on the satellite sensors satellite. So because if you use the Landsat and Sentinel, you got to know the NDVI performing much better as compared to them. So there is a kind of like wavelength variance. I haven't checked, but I will study it, so I got to know this. This is one of the.
Thank you, Satya. So that concludes our poster session on ML applications. Great thanks to Dr. Sudeepan and Dr. Ramya. And a thanks to all the presenters and participants. You guys can move to the basement for tea break. Thank you.